Welcome to this masterclass. Today, we address a provocative topic, hardware-level hacking and the rumors surrounding Anthropic Mythos' relationship with tech giants like Apple and Google. Let's separate the myths from the facts and explore how AI is actually reshaping silicon security. Let's get started. Let's immediately clarify a major misconception. There is no Anthropic plan to maliciously compromise Apple or Google silicon. In reality, Anthropic formed Project Glasswing, an elite defensive alliance that explicitly includes Apple, Google, AWS, and NVIDIA. Rather than attacking these companies, Mythos is being used by them to proactively scan and defend their infrastructure. As AWS noted, they are building defenses from our custom silicon up through the technology stack. The true danger is that if adversaries acquire similar capabilities, they could target hardware-level code, which is why these tech giants are using Mythos to find vulnerabilities before the bad guys do. This flowchart illustrates the actual relationship between Anthropic and the tech giants. Instead of an attack plan, Mythos flows through Project Glasswing to partners like Apple, Google, and AWS. They utilize the AI to scan their custom silicon and tech stacks, converging on the ultimate goal: hardened global hardware and software infrastructure. So what exactly constitutes hardware-level hacking? It refers to exploiting the low-level code, like firmware, that interfaces directly with physical silicon components. Modern cloud infrastructure relies heavily on virtual machine monitors, or VMMs, to securely isolate workloads sharing the same hardware. Hackers target these levels because a hardware or firmware compromise grants deep access that completely bypasses operating system security. How does Mythos factor in? It is highly capable of automated firmware dependency extraction and analyzing low-level memory pointers. Because code interacting with hardware must use raw memory pointers, it is inherently memory unsafe, creating vulnerabilities that AI can systematically dissect. Looking at this architectural stack, we see the application layer at the top, descending through the OS, down to the VMM and firmware layer, and finally the physical silicon. Notice how Mythos focuses its vulnerability scanning and raw pointer analysis on the VMM and firmware layers, where the software physically touches the hardware. Let's deep dive into a real-world discovery. Mythos autonomously identified a memory corruption vulnerability in a production virtual machine monitor. Even though the VMM was built using a memory-safe language, it still had to talk to the physical silicon. To do this in languages like Rust or Java, developers must use unsafe blocks or functions like sun.miscellaneous unsafe to directly manipulate raw hardware pointers. Mythos zeroed in on one of these unsafe operations and discovered a flaw that allowed an out-of-bounds write directly into the host process memory. This proves that no matter how safe the high-level language is, the hardware interface remains a critical attack vector that AI can easily exploit. This sequence diagram maps out the VMM discovery. Mythos analyzes the VMM codebase, which relies on unsafe pointer logic to interact with the hardware. By modeling this interaction, the hardware interface exposes an out-of-bounds write flaw back to the AI. Mythos then uses this intelligence to generate a potential denial of service exploit against the host. Moving deeper into the hardware realm, we encounter side-channel attacks. What are they? Instead of attacking the software, a side-channel attack extracts secrets by measuring the physical emissions of the silicon itself, such as electromagnetic waves or power fluctuations during calculations. Why is this relevant to AI? Because models like Mythos excel at deep neural network analysis. They can process the incredibly noisy data of a hardware device's electrical variations and map those patterns to reconstruct the private cryptographic key. This means the AI can steal secrets by simply listening to the silicon without ever needing to break the software encryption. Follow the data flow of a side-channel attack. The physical silicon performs a cryptographic operation, naturally emitting power and electromagnetic waves. Sensors capture this as noisy analog data. Mythos's neural analysis engine then processes this data, utilizing advanced pattern recognition to isolate the signature and reconstruct the private key entirely from hardware emissions. Another massive hardware challenge is the migration to post-quantum cryptography, or PQC. The basics are simple. New quantum-safe algorithms generate keys and signatures that are massively larger than classical cryptography. Why is this a problem? Because embedded IoT and tactical silicon have strict hardware limits. A legacy radio might only have 512 kilobytes of flash memory. Mythos is utilized here to perform automated firmware dependency extraction. It analyzes hardware constraints like maximum transmission unit limits and ROM sizes to see if the hardware can physically support the 30 to 80 kilobyte PQC libraries. If it can't, the hardware must be entirely replaced or redesigned. This block diagram highlights the physical hardware constraints during PQC migration. We have an embedded device with a strict 512 kilobyte ROM and a 256 byte MTU limit. Trying to force an 80 kilobyte PQC library and massive 3000 byte signatures into these tiny silicon boundaries results in a catastrophic hardware overload. Let's examine a critical real-time use case for defending firmware and silicon. Imagine a large telecom provider deploying thousands of third-party embedded devices. How do they know the silicon's firmware doesn't contain a backdoor? They can deploy a Mythos class AI. Mythos has the capability to take a closed source, stripped binary from the firmware and reverse engineer it into plausible source code. The AI then scans this reconstructed code, validating it against the original binary, to identify zero-day vulnerabilities buried deep in the hardware layer. This allows the enterprise to mandate immediate vendor patches or physically replace vulnerable silicon before an attacker ever discovers the flaw. The defense workflow starts by extracting the firmware binary directly from the silicon. Mythos reverse engineers this into plausible source code and conducts a deep vulnerability scan. If a zero-day is found, the enterprise immediately demands a hardware patch or replacement. If clear, the silicon is approved for deployment. While Anthropic is restricting Mythos, we must prepare for adversary AI at the hardware level. The reality is that open-weight AI models will eventually converge on these capabilities. Within months, attackers will have access to AI that can analyze firmware and silicon just as effectively. Why is this terrifying? Because countless legacy systems from SCADA industrial controllers to outdated banking mainframes rely on security by obscurity at the hardware level. Once AI exposes these flaws, the patching window for hardware vulnerabilities will collapse from months to minutes. If a piece of silicon cannot be patched over the air, it will become a permanent, exploitable liability on your network. This timeline traces the looming hardware threat. Today, Mythos is restricted. But as months pass, open-weight AI models will converge on these capabilities. Adversaries will gain the ability to analyze firmware at scale, leading to the rapid exploitation of legacy silicon and the total collapse of the traditional hardware patching window. To secure our silicon moving forward, organizations must adopt a machine-speed defense posture. First, you must aggressively audit your hardware supply chain and demand firmware visibility. Second, prioritize hardware-level isolation and begin the painful transition to memory-safe architectures, recognizing that even they have unsafe hardware interfaces. Third, you must deploy AI-native SoCs capable of detecting anomalous hardware behavior in microseconds. The rules of hardware security are being rewritten by AI. To master these advanced security concepts and prepare your career for the AI era, I invite you to like, subscribe, and visit quicktechie.com for premium certification prep, including Q&A banks, full ebooks, audiobooks, full-length training, and expert interview guides. Thank you. Our final diagram outlines the silicon security strategy. It requires a unified approach, conducting deep firmware audits, enforcing hardware isolation, migrating to memory-safe architectures, and deploying an AI-native SoC. All of these components feed directly into creating a resilient hardware ecosystem capable of withstanding next-generation AI threats.
To find related ebook and other material for this training course, go to quicktechie.com. Now you will see all the video courses are available here. So let's move to the ebooks. You can go here, ebooks, all AI related ebooks like you are watching currently Mythos related training. That ebook would be uploaded under this section. You can download this ebook. PDF would be available, all 300-page PDF. So you just click on the download this entire ebook. You can download from this section. So whatever training you are currently listening, corresponding ebook would be available. We have thousands of ebooks available. Now, other than that, we have on video courses which you are watching right now. This also all AI related courses are available. Similarly, for all company related trainings are available, like Microsoft, you can find it here with their respective certification training modules. All exam simulators which would help you to get the certification preparation. Just refresh if you get this kind of error. Okay, so now you can see these are all certification preparation materials. Will also be click here to the NVIDIA certification preparation material. So you can see all NVIDIA certification preparation materials. Click on any of this and it would load the entire screen and you can launch the practice paper. So this is what you can see, that you can submit the answer. We have an audiobooks available. Okay, so for each section, and these are our alumni who can you can find out all alumni who are accessing our portal.